Have you ever had trouble viewing a lithium sample in a microscope? The Tupperware method just not cutting it. Inaccurate results due to corrosion?
Okay.
Do I have the solution for you? Introducing the airtight flight, the newest invention being used in labs everywhere. Keeps lithium safe from corrosion using an O-ring seal and a check valve. Get your airtight flight today. Make sure it's an airtight flight.
Howdy, we are the Material Transfer Device team, and this is our Senior Design Project video. The last 2 semesters, we have been working on designing a device to transfer lithium into a scanning electron microscope, also known as an SEM, for study. Our project sponsor is Dr. Farr in the Mechanical Engineering Department, who has a focus in studying lithium. Lithium must be kept in an oxygen and moisture-free environment due to its corrosive reactions. In order to study the lithium properly inside an SEM, the samples must have as little exposure to air as possible. To achieve this, we were tasked with designing a device that would transfer the lithium from the glove box shown into an SEM without any corrosion. The basic path includes removing the lithium from the argon-filled glove box using the antechamber, or an evacuation chamber, which allows things to be transferred in and out of the glove box. Then it will be transported to the SEM stage, close inside of the SEM, and remain there until a high vacuum is achieved where it can be studied. Currently, the method is to use Tupperware to keep the lithium in an argon environment until it reaches the SEM stage. At this point, it must be taken out and exposed to air until the user can mount the sample and vacuum down the SEM. We were tasked with creating a device that will eliminate the corrosion of the lithium while it is transferred from the Tupperware to the stage. With no previous design to start with, the team decided to first brainstorm by researching other solutions and analyzing their features. Using this research, we then used multiple idea generation methods such as mind map and the 635 method to collect these ideas and come up with concepts that could be evaluated. The team decided upon 4 concepts, which were evaluated against each other to determine which one the team thought would meet all the design requirements for the sponsor while being feasible to manufacture. This led to the final concept being chosen as the ring box design shown here. The idea behind this concept was to have a lid and a base connected with a hinge and sealed together using an O-ring. A check valve, or one-way valve, will allow for the evacuation of pressure inside the device to keep it closed under atmospheric pressure, but allow it to open in a high vacuum. The team took this concept and began implementing design solutions to create the first prototype. This resulted in the first prototype shown here. The final process for the prototype is shown in this animation. The device first starts in the glove box, where the lithium is put on the base and it is closed with the lid bolts sealing argon inside, as shown by the red particles. As the device is leaving the glove box, the argon is evacuated through the check valve in the antechamber vacuum. It can now be taken to the SEM. Once at the SEM, the lid bolts can be removed since the greater atmospheric pressure outside will keep the lid closed. When the SEM vacuums down, the pressure gradient will degrade and the spring will open the lid, allowing the lithium to be viewed. After testing, the device was found to hold a vacuum seal for at least 24 hours, have usage life of 150 uses or an estimated 6 years, cost $650 to manufacture per unit, and is compatible in at least 3 test scan SEMs on the Texas A&M campus, as well as an FEI Helios focused ion beam, and the possibility to work with more equipment depending on the internal dimensions of each. This project was a success, and the team felt that we gained much more understanding of the overall design process. Thanks, and Gagum.